Hi, my name is Michael Benben, and I am in Challenge 2016 in Calculus 2000, and today we're going to be going over number 54 from Chapter 8.4, where we need to find the equation for the area of an ellipse by starting with the original equation. So the first step is to determine what that equation is, which is x squared over a squared plus y squared over b squared equals 1, and we're going to solve for y. So when we do solve for y, we end up getting b radical 1 minus x over a squared. So we're going to use this and trig substitutions now to derive ab pi, which is the equation for the area of an ellipse. Now, before actually deriving the equation, we have to simplify this equation a little bit more. So, beginning with what we have here in green from the last part, we're going to continue solving it so that we can be able to get this under the radical, which is a squared minus x squared over a squared. So then this a in the denominator can be factored out, and we're going to end up having b over a radical a squared minus x squared. Now, this under the radical is very similar to one of our trig identities. So we're going to be using that to replace these variables and be able to solve for the equation of an area of an ellipse. Now, before beginning to find this equation, we need to be able to use some trig functions to replace the elements in this equation. So we're going to be having an integral from pi to 0 as the ellipse shows, and since we're using that interval, these all the functions in here need to be relative to theta. So in order to do that, we are using our trig identities, and we can see that the sine of theta is equal to radical a squared minus x squared over a, and when we solve for it, we see that that radical is equal to a sine theta, and we can do the same to replace dx in the integral by seeing that cosine theta is equal to x over a. When we solve for x and then derive it, we get negative a sine theta d theta. So now, when we plug it all into this integral, we're able to solve for the area of an ellipse. Also, to make it easier, I'm multiplying it by 2 because this interval from pi to 0 is only half of the ellipse because we're going around it, right? So since it's half, we're multiplying it by 2, and now from here we're going to continue simplifying this integral so it becomes much easier to integrate and hopefully find the proper equation to the area of an ellipse. Now with this integral, we are going to continue simplifying it, right? So we have 2b over a is equal to the integral from 0 to pi of a squared times sine squared theta of d theta. So when we continue looking at this, we see that this a squared, it's a constant, can be taken to the front. So we have 2a squared b over a, which eventually breaks down to 2ab. And we know that sine squared theta is also equivalent to 1 minus cosine 2 theta over 2. So that's going to make it much easier for us to integrate. By splitting up that fraction and then factoring out the 1/2, we can see that it's going to be 2ab times the integral of 0 to pi of 1/2 1 minus cosine 2 theta of d theta. This 1/2 is also going to be taken out to the front, where we'll eventually just have ab times the integral. And then now, since it's simplified enough, we can finally integrate the parts of this function and see that we should be getting the equation for the area of an ellipse. Now we're finally integrating this function, right? So 1 becomes theta, and cosine 2 theta becomes 1 over 2 sine of 2 theta. When we plug in the intervals, we end up getting pi minus 1/2 sine of 2 pi, which is 0, minus 0, minus 1 over 2 sine of 0, which is also 0. So in the end, we get ab pi, which is the area of an ellipse, which we just derived from the general equation for an ellipse. And that will be it for number 54 from chapter 8.4. And I'll see you in the next video.